The purpose of this course is to give you some tools, conceptual tools from the Philosopher's Toolkit. Tools for effective problem solving, for logical thinking, tools for rationality in general. In this lecture, I want to give you what I think is the most important tool of all. If I could hand you just one tool for logical thinking and effective problem solving, this would be it. The tool of visualization. Some of the lectures in this course work best if you can participate with pencil and paper along the way. This is one of those. If you can't work with pencil and paper right now, go on to another lecture and come back to this one. Visualization. I'll start with an example that I want you to do entirely in your head. You've got a long rectangular board. You cut it into two lengths, one of which is 3 times the length of the other. You now cut the smaller of those again into 2 pieces, one of which is twice as long as the other. The smallest piece is now 8 inches square. How long was the board you started out with? If you're like me, that's a medium grade problem. Not impossible, but it's easy to get lost. Now I want you to draw the board. Draw a long rectangular board, divided into 2 lengths, one of which is 3 times the length of the other. You'll draw a board with 4 equal parts. The smaller of those parts is cut into 2 pieces, one of which is twice as long as the other. If you draw it, your picture will probably show that smaller piece divided into 3. The smallest piece of all is now 8 inches square. How long was the board? Looking at that picture, the answer is pretty obvious. The bit you divided into 3 has to be 3 times the length of your 8-inch square. So it's 24 inches long. The original board has to be 4 times that, 96 inches or 8 feet long. When you try to do it in your head, it's complicated, but not when you can see it. Not even when you can see it in your mind's eye. When you try to do it in your head, it's mathy. You end up with all those symbols. But it's a lot less mathy, a lot less intimidating when you can see it. Then it's just a picture. If you're like me, pictures are a lot easier to think with than symbols are. I'm not out to teach you visualization. It's a tool you already have. What I want to do is to increase your respect for that tool, to use it more, to put it to work. There's something that people are extremely good at, but computers aren't. What we're particularly good at is pattern recognition. Think of your ability to recognize human faces. Newborns don't have any trouble recognizing a face as a face. We don't have any trouble recognizing the face of someone we know. We can sometimes do that even if we haven't seen the person for 20 years. Even if they're older, they've grown a mustache, and we see them fleetingly through a train window. Computer scientists have been trying to replicate that ability for decades. When it comes to information processing and pattern recognition, we have an amazingly fast and accurate resource at our disposal. Computers are faster and more accurate at all kinds of symbolic calculation. But when it comes to information processing and pattern recognition, nothing beats our visual system. Herbert Simon was a major figure in both computer science and cognitive science. In a paper called Why a Diagram is Sometimes Worth 10,000 Words, he compares side by side a purely symbolic approach to a problem and an approach that uses a diagram. The symbolic approach runs to several detailed pages. The diagram, it turns out, is both more efficient and more convincing. Why is the diagram better? Simon thinks it's because we can see it, and seeing it allows us to exploit the visual thinking that's built in. Seeing it allows us to draw the immediate visual inferences that people are so good at. There's a long history of visualization in the Philosopher's Toolkit. At the core of the Republic, Plato outlines a theory of the relation between the visible and the intelligible world, between mere opinion and genuine knowledge. How does he try to get that across? visually, with a diagram. It's called Plato's divided line, divided between the visible and the intelligible, further divided on each side between superficial understanding and a deeper grasp. One can almost see Plato scratching that line in the Athenian sand, and I'm sure he did. Of course, Plato wasn't the first. Before Plato came Pythagoras, philosopher, mystic, and mathematician. Everyone knows the Pythagorean theorem. For any right triangle, the square of the hypotenuse is equal to the sum of the squares on the other two sides. Well, almost everybody knows it. At the end of The Wizard of Oz, the Scarecrow shows off his new brain by saying, the sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. That's just so wrong in so many ways. No, for any right triangle, the square of the hypotenuse is equal to the sum of the squares on the other two sides. The Pythagorean theorem is the shining gem in Euclid's geometry. In geometry, you may have proven the Pythagorean theorem from axioms, as Euclid did. But it's pretty clear that Pythagoras didn't think of it in terms of axioms. The source of his insight was almost certainly visual. In the last part of the lecture, I'll show you what Pythagoras' proof might have looked like. He almost certainly proved it by manipulating shapes with simply the power of visualization. Pythagoras' insight was literally something that he saw. That tradition of visualization continues through the history of thought. Another philosopher-mathematician, René Descartes, saw that there was a link between equations like y equals 2x squared plus 9x plus 3 and the beautiful arc of a parabola. By treating x and y as coordinates in a plane, algebra becomes geometrically visual. We still call those Cartesian coordinates. The conceptual tool, visualization. Why does it help to work with pencil and paper rather than entirely in your head? One reason is cognitive capacity. There are just so many things we can hold in conscious attention at one time. I'll give you two numbers. I want you to multiply them in your head. The numbers are 9 and 7. That was easy, right? 63. Here are two more numbers. Now multiply these in your head. 27 and 54. Ouch! If you got that, I'm sure it took longer. The number is 1,458. Let me give you a third pair of numbers. 259 and 376. Unless you're a savant, that would take longer. It would hurt even more, and your error rate would rise. One of the most cited papers in psychology is a classic from the 1950s by George Miller, The Magical Number 7 plus or minus 2, Some Limits on Our Capacity for Processing Information. The thesis is that we can only manage about 7 pieces of information at one time, plus or minus 2. That's the limit of a phone number without the area code. Not surprisingly, the 7 plus or minus thesis depends on context, on what the 7 items are, and how you chunk information. The truth is, there's no single magic number that measures human cognitive capacity. But Miller makes his point. Our cognitive grasp is limited. It's probably much more limited than we'd like to think. You run up against that capacity when you try to multiply 2 3-digit numbers in your head. But now do something different. Write the 2 numbers down. 259 and 376. Multiply them on paper. That's going to be no problem at all. It'll take a minute, particularly since we're so used to grabbing a calculator, but with pencil and paper, it's easy. One benefit of writing it out is that it frees up cognitive load. If you assign the memory function to a piece of paper, you can let your brain concentrate on the manipulation function, like doing the actual multiplication. But visualization has benefits far beyond memory. Sometimes a visualization can practically solve the problem by itself. Here's a problem like that. There are 5 roads in Brown County. One runs from Abbeville to Brownsville by way of Clinton. One runs from Clinton to Derbyshire by way of Fremont. One runs from Fremont to Brownsville by way of Abbeville. That's all the roads in Brown County and all the roads in and out of those towns. Now let me give you 3 questions. Which towns have roads connecting them directly to 3 other towns? Which towns have roads connecting them directly to only 2 other towns? And how many towns do you have to pass through to get from Brownsville to Derbyshire? If you want to try those, press pause for a minute and start again when you're ready. If you've been paying attention to the theme of this lecture, you work those problems out by making a sketch. Indeed, I don't know why anyone would try to handle that kind of complexity without a sketch. 2 things happen with a sketch. The first is the simple matter of memory. Once you codify each piece of information in the sketch, you no longer have to keep it in short-term memory. Was that Abbeville to Clinton by way of Brownsville, or Abbeville to Brownsville by way of Clinton? The other thing that happens is that the sketch practically solves the problem by itself because the information is all in the sketch. You can supply the information asked for just by looking at it. Which towns have roads leading directly to 3 other towns? Abbeville, Clinton, and Fremont. Which towns have roads connecting directly to just 2 others? Just Brownsville. How many towns between Brownsville and Derbyshire? 2, by 2 separate routes, though you could also go through 3 towns if you wanted to. The diagram itself embodies the information you need. The sketch itself solves the problem. You can use visualization for more abstract problems as well. Here's one. Each of 4 students, boys Jacob and Eli, and girls Lauren and Molly, got a different passing grade on a quiz, A, B, C, or D. Both boys scored lower than Lauren. Eli got a B. The problem gives us that information about kids and grades and asks us to answer some further questions. What grade did Lauren get? If the girls got both the best grade and the worst grade, what grade did Jacob get? If both boys had scored less than both girls, which of the initial statements I just gave you would have to be false? This is really a problem in information management. Use the information you have in order to squeeze out some more. And here again, visualization is the key. Even though the tie between people and grades is more abstract than roads between towns. What I just gave you is a common type of problem on standardized tests. It's known as a matrix problem because it's most easily solved with a particular visualization, a rectangular array called a matrix. The question's really about how 2 things align. Students Jacob, Eli, Lauren, and Molly on the one hand, and the grades A, B, C, and D on the other. Visualization turns that abstract alignment into a spatial one. A checkerboard matrix with the grades lined up along the top and the student names down the side. Spatial arrangements, spatial relationships, are easier to handle than abstract ones. You can see them. To solve the problem, we enter the information we have and read off the information we need. The 3 questions draw on the basic information we've been given. We get that down first. You should be aware that problems like this don't guarantee complete information. We want to tack down the information we have, see what possibilities that leaves open, and then turn to the particular questions asked. So draw the grid, solve the problem, and come back. I'll be here working on it too. So let's think this through on the matrix. Start with the pieces of information that are most specific and seem to offer an immediate payoff. It was the second piece of information that we were given, but Eli got a B is the most promising. Let's use a dot to indicate positive information. That Eli got a B. We drop that in the matrix. We'll use an X to indicate negative information. Since Eli got a B, we know he didn't get some other grade, so X those out. Since we know that each student got a different grade, we know that no one else got a B. X those out. Our matrix just got smaller. We filled in a lot of information with that one bit. Now enter the rest of our information. Both boys scored lower than Lauren. Well, that doesn't tell us what both boys scored, but it does tell us what Lauren scored. Eli is a boy. Lauren did better than both boys, so Lauren had to get an A. Fill in the positive information. Now, fill in the negative information. That's all the information we have. But now it's visual. We can literally see what we know and what we don't. So what about those two other questions? If the girls got both the best grade and the worst grade, what grade did Jacob get? Since Lauren got an A, that would mean that Molly got a D. That would X out everything on the graph except for one slot left for Jacob. He'd have to get the C. And how about that last question? If both boys had scored less than both girls, which of the initial statements would have to be false? Well, it wouldn't have to be false that both boys scored less than Lauren. In fact, that would have to be true. But it couldn't be true that Eli got a B unless more than one student got the same grade. So in that case, one of these initial pieces of information would have to be false, either that Eli got a B or that each student got a different grade. As I say, that type of problem is a favorite in standardized testing. But the key is simply a particular kind of visualization. With the right representation, the abstract becomes spatial. When you approach it visually, the problem is easy. People can train themselves in certain types of visualization and even in certain types of seeing. I'm sure this is true of chess masters, who can see the significance of board patterns that are invisible to the rest of us. An easy example is what's called an open file, a sequence of squares that are vacant, open to a rook or a queen, for example, running from the player's side of the board toward the opponent's. What mastery demands is being able to visualize the board not in terms of where pieces are, but where they can go, or even in terms of fields of force. That leads me to another sense in which people talk about visualization. People sometimes talk about visualization as picturing what you want and claim that that'll help you get what you want. I'm not sure that'll work as a general technique. You can visualize being handed $1 million tomorrow all you like. I don't think that'll make it happen. But the story is told that the comedian Jim Carrey, still a struggling Canadian comic in the mid-1980s, wrote himself a check for $10 million for acting services rendered, dated years into the future. He carried that check for years as a focus, an inspiration, and a promise to himself. Mentally rehearsing a musical passage can indeed make you better at it. Mentally envisaging how your tennis serve should look can help you make it that way. But of course, mental rehearsal isn't the whole story. You have to pick up that tennis racket to put your visualization to work. Einstein was one of the great visualizers. He said he never thought in symbols or equations, that he thought in images, feelings, even musical architectures instead. The images, he said, came first. The words came later. In thinking through relativity theory, he envisaged lightning strikes hitting the ends of a moving train. He asked himself what the timing of the strikes would look like to someone inside the train, and how they'd look to someone watching the train from the outside. That visualization is part of a thought experiment I'll explore in a later lecture. Einstein also employed much more abstract visualizations. He talks of gravity bending light, for example, and speaks of the curvature of space-time. It's become common to visualize those things in terms of a bowling ball on a rubber sheet. If you think of space as a square grid on a rubber sheet, what happens with light around massive bodies is something like what that grid looks like when you drop a bowling ball in the middle. The gravitational force makes straight lines curved just as light will curve around a massive body. That image ties in with one of the first and most dramatic tests of some of Einstein's work. Suppose gravity does bend light. Then the observed position of some distant source of light, like the stars, should be different when there is and isn't a massive body between us and them, like the sun. If we could photograph the stars in an area of the sky when A, the sun is next to them, and B, when it isn't, and compare those photographs, we should be able to see if the theory is true. Unfortunately, you can't see the stars next to the sun. The sun's too bright. You can see them, however, during a total eclipse. In 1919, the British astronomer Arthur Eddington organized expeditions to Africa and Brazil in order to photograph the same portion of the sky before and during an eclipse. He was able to display the variance in the plates as a vindication of Einstein's vision. Philosophers of science still talk about that expedition, in part because Eddington may have glossed over some ambiguities in the data. What no one denies is how productive that visualization of curved space-time has turned out to be. The phenomenon is now called gravitational lensing. Sometimes, Einstein's visualizations were intended to explore even the limits of possibility. This is how Einstein himself portrayed one of his earliest visualizations. At the age of 16, he tells us, he tried to visualize what he would see if he pursued a beam of light with the speed of light. In that childlike thought experiment, he says, one can already see the germ of relativity theory. In that context, he again emphasizes visualization. Quote, discovery is not a work of logical thought, even if the final product is bound in logical form. There's an interesting footnote here. How did Einstein acquire his mastery of visualization? At 16, he was a student at the Aarau School. The teaching at Aarau was based on the work of an educational reformer named Pestalozzi. What Pestalozzi wrote was that the learning of numbers and language must be definitely subordinated. Visual understanding is the essential and only true means of teaching how to judge things correctly. An emphasis on visualization was an explicit part of Einstein's education. Let me return to Pythagoras. The Pythagorean theorem has been called the single most important result in all of mathematics. And yet Pythagoras' proof was almost certainly visual, using no math at all. First, the theorem the way Pythagoras probably saw it. For any right triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides. For square, don't think of mathy things like numbers raised to the power of 2. For square, just think square. The triangle in the middle is a right triangle, any right triangle. That large square on the upper right is the square on the hypotenuse. And what the theorem says is just that the area of that square is the same as the sum of the area of the other two squares put together, always. Pythagoras' visual proof probably went something like this. Take that square on the hypotenuse. Because it's a square, and because they're right triangles, we can fold 4 of these into that square, like this. Those cover the square on the hypotenuse, except for a little square in the middle, which you'll notice has sides that are the difference between the long side and the short side of our original triangle. When we put that in the square, we've covered the area of the square on the hypotenuse. What we want to show is that that area is the same as these other two put together. Now, because that's the area of the square on the hypotenuse, that area will remain the same even if we rearrange the pieces. Same area, rearranged. What we're out to show is that that area is the same as the area of these two squares put together. Take the little one. Its edge is the same as this edge over here. It'll cover that area first. Now take this one over here. This is the same as the long edge of our triangle, with this difference between the short and the long edge added in. That covers this area perfectly. There you have it. The square on the hypotenuse equals the sum of the squares on the other two sides. Nothing in that visual proof depended on what kind of right triangle it was, so it'll work for them all. Pythagoras himself saw the importance of the result. It is said that he sacrificed 100 oxen in celebration. What I hope you'll take from this lecture isn't so much a thesis as a tool, or increased respect for a tool you already have. Your thinking isn't limited to the space between your ears. There's no reason not to think of thinking as something that can happen using your eyes and with pencil and a piece of paper in front of you. Thinking can indeed be more powerful in that format. Mental visualization is very much like that. There's been a lot of work done in psychology on what's called mental rotation. In two-dimensional form, you are given two shape silhouettes and are asked whether it's possible to convert one into the other by rotating them. Which of the shapes on the right are rotations of the ones on the left? In three-dimensional form, you're given two three-dimensional shapes and asked whether the shapes are the same but somehow rotated. Which of the shapes on the right here are rotations of the ones on the left? It's been found that the time it takes someone to discover whether two rotated shapes are the same is directly related to how far you'd have to turn one in order to get the other. Just as it's faster to rotate something 90 degrees than a full 180 degrees, people are faster at recognizing something as rotated 90 degrees than a full 180 degrees. Another interesting result is that some of the same portions of the brain that are used in actual rotation are used in imagined or mental rotation. Seeing and imagining recruit some of the same crucial brain circuits. Did you get those, by the way? For the first one, rotation will give you the second and the fourth images. For the second one, it's the first and the third. The last interesting result is perhaps the most important for this lecture. Like all forms of visualization, mental rotation is something that gets better with practice. In the next lecture, we'll put these tools of visualization to work in examining the fundamental elements of all reasoning, the atoms of thought.